Hi, I'm Dan Abel, and in this lesson, we're going to calculate current based on charge flow. So, before we calculate current, it's important to understand that current's a flow rate. And what that means is it's the number of charges per second. And this is different from the idea of velocity. So, flow rate is not the same thing as velocity. And a good example of this is thinking about a river. You can have a really thin stream that's going really fast, and that can get the same amount of water past a point as a really wide river that's going very slow. In this case, the velocities are different, but because that slow river is so wide, I can have the same flow rate, the same amount of water per second. So that's why it's defined mathematically as delta Q over delta T, where delta Q is the charge, the amount of charge that flows past, and delta T is the amount of time that it takes for that charge to flow past. We measure current in amp or amperes. 1 amp is 1 coulomb of charge going by every second. And that's a lot of charge because one proton or one electron has a charge of 1.6 times 10 to the minus 19 coulombs. So it's going to take a heck of a lot of electrons flowing past a point to get 1 amp of current. Let's put this into practice with some calculation questions. So in this problem, we are told that we have a certain number of sodium ions, 1.5 times 10 to the 18th, flowing into the axon every 3 seconds. We want to determine the current. So we're going to go back to our relationship. Current is amount of charge per time, but we're not given the amount of charge. We're given the number of ions. And so we have to do a little bit of extra work here to convert number of ions to amount of charge by knowing the amount of charge that each ion carries. Sodium is singly ionized, meaning that it's got one extra proton. And so we know that there are 1.6 times 10 to the minus 19 coulombs in each extra proton, which means that there's that many coulombs per sodium ion. So we're going to take our number of ions and we're going to multiply by charge per ion. That will cancel out ions and leave us with amount of charge. We can then take that amount of charge, which is 0.24 coulombs, and divide by the number of seconds, 3 seconds, to get that there's a total of 0.08 amps of current flowing into this axon every 3 seconds. So this is an example of positive charge flow, which is the direction of the conventional current. In part B, we see an example of negative charge flow. We have a wire carrying a current of 1.2 amps. How many electrons pass by the wire in 2 minutes? Now, the 1.2 amps is positive charge flow, but because of what we looked at back in lesson 6.1 about the direction of charge flow, we know that positive current moving one way is equivalent to negative current moving the other way. So we can think of this as 1.2 amps of positive current or 1.2 amps of negative current moving the other way. So we're going to use our same relationship, and we have 1.2 amps and 120 seconds. Now we have to turn 2 minutes into 120 seconds because amps is charge per second. That allows us to solve for a Q of 144 coulombs of charge. But we're not asked for the amount of charge, we're asked for the number of electrons. So this is almost going backwards from the problem in part A. In A, we had the number of charges, and we had to find the total charge. Here we have the total charge, and we're going to convert that to number of electrons, again, using the idea that one electron is 1.6 times 10 to the minus 19 coulombs. And so a little quick math there, and we get 9 times 10 to the 20th electrons will pass by a point in the wire every 2 minutes. So in the previous two examples, we've been using the definition of current, amount of charge per second, to calculate the current directly, or given the current to calculate the amount of charge flowing by a point. In a later lesson, we're going to see that in a circuit, sometimes we know the voltage and the resistance, and from there can calculate the current using Ohm's law.